Okay, so you should be correcting this in red on your paper. And as soon as someone is ready or has something they need to say, I will answer any questions or talk about any answers that you need me to go over. So I see writing, but nobody's really telling me what You're supposed to be correcting your paper, and then whatever you need me to explain because you don't understand or you missed, you're going to say you need me to go over it. And so I'm just waiting. I see you writing. If y'all want to write everything first and then tell me, that's fine. Gabby? Okay, that's where everybody's having a little bit of trouble. Okay, let's think about this, though. If the swinging is the action, okay, let's say she swings but she doesn't make contact. There's no reaction. The swinging is not what causes it. Yes, she's got to move it, but where's the force actually come from? When the club makes the contact. Does that make sense? Well, yeah, you hit it, but the hit when the club touches the ball, right? It's going to put a force on it, and the ball's going to actually put a force back on the club. Well, then put the club. You're supposed to be fixing your answers. The weird thing, okay, sorry. Law 3, guys, it sounds kind of weird, but Law 3 is how you know that you're even touching anything. Like even you holding your pen or your pencil, whatever. You actually being able to feel it, that's because that other thing, even though it's so tiny, is putting a force back on you. That's how you feel things. That's how you feel things. You know that you've touched it because whenever you do, you're putting a force on it, and it's actually putting a force on you in the opposite direction.
So it's like whenever you squeeze something and you feel
It's not just it's not just that. Here, holding your pencil, holding something. How do you can feel it. Yeah, you can feel it because when you're putting that force on it, it's putting the force back on you. The opposite direction. Yes?
What is the thing that's pushing back on you or something?
That object. That exact object. Yes. No, you're putting a force to hold it. Like my force is up on the pen and the pen's putting a force back down on me. I'm not moving it. I'm going to put it where you can see it.
So it's basically normal force, but on an object, not on the surface?
Yeah, any object can have a normal force. But it's from the surface of the object, which if I'm holding it like this, that surface is right there where it's making contact. Yes?
So I put from pushing off the little pad?
He doesn't push off. He pushes down. The lily pad pushes him off. If the lily pad didn't, when he pushed down, he'd sink.
When something's heavier, it has too much mass for you to carry, is that like the object pushing back? Or is that just...
No, I mean, you're still putting a force on it. You just can't, if you can't lift it, then you can't overcome the, like the gravity that's holding it there, basically. But if you can, then whatever force you're lifting it with, it's still putting that force back on your hands.
Number 3 on the reaction, I put the lily pad and pushed off.
The lily pad is pushed opposite? No. The frog, okay. That's the lily pad. That's the frog. Okay? The frog, his feet right there, he's going to push down, right? Like that. When he pushes down on that lily pad right there, the lily pad is going to push in the opposite direction back on him with the same amount of force. So he ends up flying up here. Yes, sir.
On number 1, I puts her arm out and pushes.
The child on the right, the first person pushes. Yeah, you can put that. Okay? Yes.
Number 2, I put the golfer swings. Is that
I've already explained that. The swinging, like I could swing and miss the ball. That's not going to cause the reaction. It's when the contact is made. Yes.
Just like the bat.
Yes, it's just like batting. Okay. Wait, before we start, hang on. Listen. What kind of makes it a little confusing is every example can be all 3 laws. Every example can be all 3 laws. This rocket is not going to go anywhere until it has an unbalanced force to make it move. Or once it's moving, it's going to keep moving until it has an unbalanced force. Okay, that's law 1. Law 2. The harder that the rockets push, the more that it's going to accelerate. If I don't push hard enough, I'm not going to accelerate very far. That's law 2. Force, mass, acceleration. Law 3. When the rockets push down on the ground pushes up in the opposite direction. That's how it lifts. Okay? So it's all 3 laws. You have to pay attention to the words that are used in each one. Here we go.
Is it impossible for something to happen when all 3 laws actually?
They don't happen at the same time. Because law 1 is unbalanced forces, but law 3 is balanced. And then acceleration, for acceleration to occur, I have to have unbalanced forces. Yes?
If you were to give us a picture like this and say which law,
I can't do that. I can't do that.
The answer wouldn't be wrong if you could.
Yeah, I can't do that.
Because you don't know which one.
Yeah, that's why it's not going to be like that.
It'd be like a bone.
That's why it's going to be, I'm going to use the verbiage of that law, and it should stick out to you which one I'm referring to. What else do I need to explain? Yes, I'm sorry.
You can get the laws mixed up. I put these stops and the rocket was between, I made the rocket was between. What does that say?
Where are you putting that? On number 1, the first law, You could say that the rocket keeps going until an unbalanced force acts on it.
I thought it saved him on this.
Yeah, you can say it. Law 1. An object at rest stays at rest. Or an object in motion stays in motion unless acted on by an unbalanced force. It can go either way.
On number 2, I put it pushing on the surface and the surface pushes back.
What surface are you talking about?
I can't see.
I don't mind you putting that, but I need you to know what the surface is. Do you know? The ground. So scratch out your surface word and put the ground, and that's okay. Carter.
So number 2.
Yep.
Did I get this one right? When the fire blows, the rocket moves.
Okay, you are right, but do you know why that happens?
Because
Not really. The fire pushes on the ground, and then the rocket moves up. So if you change your words in there to say that the fire pushes on the ground and that the rocket moves up, that fits. Anthony.
Is it better the rocket was continually returning back to the
Yeah, that's good. Can I move off of the rocket now?
Yes, ma'am.
What else? What you looking at? None? You're good? Riley? Anything? Heather?
I put that the motor on the moving so it will continue to move until the water stops.
Okay, I mean, that fits my second sentence, really. Can you add in that it would stay at rest until he paddles, though, please? Yes.
Is there one for second and player gets of the other players so they're in opposite direction?
Make that where I can understand that a little bit better. What are you saying?
It's the number 8 times the number 8 gets the other guy sitting in the opposite direction.
No, that's not. Okay. You're mixing two laws right there. Can I explain this to you? Hang on. Don't look at your paper again because you're getting overwhelmed. You're mixing two things right there because really this part is going to explain their initial contact. Okay? Because according to Law 2, I'm going to accelerate him to the ground. And if I accelerate him to the ground, then I have to push harder. Does that make sense? We got to separate these two things. Law 2 is I need more force to get him to the ground. But according to Law 3, do I have somebody that makes more force than the other? No, not in Law 3. So Law 3 is what's going to happen when they go to make the tackle. When I go to make the tackle, he's going to push on him, and he's going to push him with the same amount of force. And they could stay like that if it were balanced, but that's probably not what's going to happen. He's going to accelerate him to the ground, so then it becomes Law 2. He's got to have more force to accelerate him to the ground. They should have switched the order of those on that worksheet. Yes, sir. Yes. That would be right. Heather.
For number 6, the water, he pushes the water sometimes.
No. It's the harder that I paddle, the more acceleration that I'm going to have. Like, think about it, y'all. If you're in the boat and you barely paddle, are you going anywhere? No. That's what Law 2 says. How is the boat Law 3? Go, Tate. The paddle pushes, well, yeah, I push the paddle, not harder. I push the paddle backwards, but the boat goes forwards. So I'm going to push the water that way, and the water's going to push me that way, back, the opposite direction. You got to talk about, when you're talking about the second law, you've got to talk about force, mass, acceleration. The mass is not changing. So we're talking about force and acceleration. How hard he paddles is how much he's going to accelerate.
Number 6, I put he is the mass, the paddle is the force, and the boat is the acceleration.
The boat will accelerate. The boat. How much he paddles determines my acceleration. Does that make sense? All right. Grab force and acceleration problems. We are still in red. We are still writing in red. When two letters boys. It was for homework a long time ago. It was actually for homework last Thursday, and if you didn't do it last Thursday, I put it on the board again for Friday over the weekend. Yeah, I know. Okay, when two letters are side by side, they automatically mean multiply. So I don't have to write the multiplication sign. You actually can't write an X in there.
I didn't put an X, I put a dot.
Well, I did put a dot right there.
If we did that, that's your glasses.
You cannot put an X.
If we put a dot, would you line it up, or do we put M-A?
M-A. You put the dot in there.
Miss Brooke,
Yes,
I
ma'am.
think Kalacia Jennings in the office to check out.
She's in the band thing.
Okay, thank you.
Yes, sir. Okay, the thing with number 3 is it's talking about a falling rock. Okay? When anything falls, what's the rate that it accelerates at? 9.8 meters per second squared. So that you had to remember that it's 9.8 meters per second squared as it falls. Yes.
Always have to capitalize F. That's why I got those wrong. So the only thing I got wrong.
Acceleration due to gravity. Look. This is a ping pong ball and a golf ball. They're released at the same time. They fall at the same rate. They hit the ground at the same time. Hang on. I'm going to explain it to you another way. Hang on. Let me show you this picture. Okay. Look. Anthony, right here. 1 second, 9.8 meters per second. At 2 seconds, it's at 19.6. So 9.8 plus 9.8 is, it's every time I move a second, I increase it by 9.8. Oh, go to 3 seconds. 29.4. What it means is, gravity makes things move at 9.8 meters per second every second. Okay? So, Carter, let me explain this to you in another way. Let's take Carter. We're going to send him downstairs. You're going to stand in the courtyard right below my window. Okay? And I'm going to be at that window, and I've got a tennis ball or a golf, let's say I got a golf ball and a bowling ball. Okay? I'm going to drop them. They're going to hit you at the same time. But you get to choose if you want to be on the side with the golf ball or the bowling ball.
I'll take the golf ball.
I would choose the golf ball. Okay? So, according to the second law of motion, they're going to accelerate at the same rate, both going to go at 9.8 meters per second squared. They're going to hit at the same time, but they're not going to hit with the same force. If we worked, y'all quit talking, please. I'm about to send everybody back to their seats. If you can't see, I can't help you. You can't keep your mouth closed. So, if we had to calculate that, both of them, F equals MA equals, let's say the mass of the golf ball is 100 grams times 9.8 meters per second squared. F equals MA. Let's say the mass of the bowling ball is 10,000 grams times 9.8 meters per second squared. Which one's going to have more force? Bowling ball. They're going to hit the ground at the same time, but he's going to pack a punch. Make sense? Okay. Any other questions on this worksheet? Okay, well, now you see, because units will count. No, it's comma. Okay. All red pencils are put up. Get this out. Okay, so you should now have your pencil. This is the page that will be graded in the packet. I'm going to explain it to you very quickly. Number one thing that we are doing, handy dandy triangle at the top right now. Matthew, we picked it up when we walked in the door, and I am ready to begin, and you're going to be behind me. So, when a letter is on top of another letter, we divide, and when two letters are side by side, we multiply. Now, Miss Fuselaire made this paper for us, and she made it very easy. Because you are going to fill in the blanks, and it makes it obvious what we're trying to calculate. What net force is required to accelerate a car at a rate of 2 meters per second squared if the car has a mass of 3,000 kilograms? So, first thing I need to do, fill in any of the known items in the sentence. So, what do you see? 3,000 kilograms, where does that go? Mass. You should have 3,000 kilograms there. What else do we know in the sentence? 2 meters per second squared is acceleration. You should put it in this blank right there. That means my empty blank is F. So I go to my triangle, I cover up the F, mass times acceleration. So, you've got to come down here. I have not been grading your work. I am today. This paper, the work gets graded. It is worth points. So if you don't do it, you will fail. First thing you have to do is write out the full formula with the letters. The second step, put the numbers where they go. So if the formula says M, what goes right here?
3,000 grams.
3,000 kilograms. The next letter is A. What am I putting right here? 2 meters per second squared. Then I will do that times that equals 6,000 newtons. And you've got to put it in the blank. It has to have the units. Okay? So your work will be graded. Your work will be graded. This is not homework. Do not finish it for homework. Your homework is to get my laws memorized so we can do our cards tomorrow. Okay? You're using whatever time you have left in class to work on this paper. Do not pick your head up. Go. Wherever.